When work is done against a conservative force, like gravitational force, it gets stored as potential energy. Let's consider a body lifted vertically to a height h from the surface of the Earth. Some work needs to be done against the gravitational force of the Earth to lift the body, which is stored as potential energy in the body. When the body is released from height h, the body gains kinetic energy and loses an equal amount of potential energy. The law of conservation of energy holds good in this case, as the total energy of the system is constant. Like gravitational force, the electrostatic force between two charges at rest, expressed by Coulomb's law, is also a conservative force. The gravitational force between masses m1 and m2, separated by a distance d, is expressed as g into m1 m2 by d square, where g is the universal gravitational constant, which is equal to 6.67 into 10 raised to the power minus 11 Newton meter square per kilogram square. We can see that the gravitational force F is inversely proportional to the square of the distance d between the masses. Similarly, the Coulomb or the electrostatic force F between charges Q1 and Q2, separated by a distance d, is expressed as K into Q1 Q2 by d square, where K is a constant which is equal to 1 by 4 pi epsilon naught. We can say that the electrostatic force F is inversely proportional to the square of the distance d between the charges. When a force acting between two bodies is inversely proportional to the square of the distance between them, that force is said to be obeying the inverse square law. We observe that both gravitational force and electrostatic force obey the inverse square law. We know that work done against gravitational force is stored as gravitational potential energy for the mass in the gravitational field. Similarly, work done against electrostatic force is stored as electrostatic potential energy in a charged particle in an electric field. Let us now discuss the electrostatic potential energy of a charged particle in an electric field. Consider the electric field of a positive charge Q placed at the origin O. Let Q0 be a positive test charge located at point S. To bring the charge Q0 from point S to a point P closer to charge Q, some work has to be done against the force due to the electrostatic field Fe. The external force F required to move Q0 should be just about sufficient to overcome the electrostatic repulsive force Fe on Q0. Therefore, we can say that the magnitude of the external force F is equal to the magnitude of Fe. Let this be equation 1. The external force F should not give the charge Q0 any acceleration. The net force on Q0 must be 0. The charge Q0 must be brought from point S to point P at a very low constant speed. The work done to move Q0 from point S to point P is denoted by WSP and is stored as electrostatic potential energy for charge Q0. If we remove the external force F, then the charge Q0 moves away from Q in the direction of the electric field and gains kinetic energy such that the gain in kinetic energy is equal to the loss in its electrostatic potential energy. the sum of the kinetic and electrostatic potential energies of charge Q0 is always a constant or conserved. We know that the work done by the external force F to move charge Q0 from point S to P is denoted by WSP. This is equal to the integral of external force F dot dr in the limits S to P, where dr is the distance between the 2 points. Let this be equation 2. From equation 1, we know that the magnitude of the external force F is equal to the magnitude of force Fe due to the electric field. But the direction of the electrostatic force of Fe is opposite to that of the external force F. Therefore, we can say that external force F is equal to minus Fe. Let this be equation 3. Substituting the value of the external force F from equation 3 in equation 2, we get WSP is equal to minus integral Fe dot dr in the limits S to P. Let this be equation 4. In equation 4, the work done against the electrostatic force is stored as electrostatic potential energy. Hence, at every point in the electric field, the charge Q0 possesses electrostatic potential energy. Let the potential energy of the charge Q0 at points P and S be UP and US respectively. The work done by the external force F, as given by equation 4, is also equal to the difference in the electrostatic potential energies of the charge Q0 at the points P and S in the electric field. Let this be equation 5. The work done by the external force F is WSP is equal to delta U. Let this be equation 6. From equations 5 and 6, the work done by the external force WSP can be rewritten as delta U is equal to UP minus US. Let this be equation 7. The difference in electrostatic potential energy between 2 points in the electric field of any arbitrary charge distribution will be equal to the work done to move a charge from one point to another. The work done according to equation 7 is independent of the path followed to move Q0 from S to P without accelerating Q0, and is dependent only on the initial and final positions. Hence, the electrostatic force Fe is a conservative force, and the work done against the electrostatic force Fe is independent of the path followed. Adding a constant C to the electrostatic potential energy at points S and P will not alter the values of the difference in electrostatic potential energy between the charges and the work done WSP. Hence, we can choose a convenient reference point where the value of the potential energy is 0. Let point S be at an infinite distance from the charge Q. The electrostatic potential energy of Q0 at point S is US equal to U infinity is 0. Therefore, the work done according to equation 7 can be rewritten as WSP is equal to UP minus U infinity, which can be written as WSP is equal to UP since electrostatic potential energy at infinity is equal to 0. That is, U infinity is equal to 0. Let this be equation 8. Based on equation 8, the electrostatic potential energy of a charge Q0 can be defined as the work done by an external force to bring a charge Q0 from infinity to a point in the electric field of any charge distribution is equal to the electrostatic potential energy of the charge Q0 at that point. A parallel plate capacitor consists of two metal plates, each of area A and separated by a distance D. When the plates of the capacitor are connected to a battery, one of the plates is given an excess charge plus Q, and the other is given an excess charge minus Q. Due to this, a uniform electric field is created between the plates of the capacitors. Towards the edges of the plates, we observe fringing in the electric field. That is, the field is non-uniform when the plates of the capacitor are separated by some distance. We know that D is the distance between the plates. But if D square is very less compared to the value of the area A, the fringing effects can be neglected in the regions which are far off from the edges of the plates. Let the magnitude of the charge density be sigma for the plates with a charge Q on them. Then, sigma is equal to Q by A. Let this be equation 1. Let us assume the region on the left side of the capacitor as region 1, region between the plates as region 2, and the region to the right side of the capacitor as region 3. Let us now calculate the electric field in the regions 1, 2 and 3 with respect to the capacitor. We do this by applying the Gauss law to calculate the electric field in the regions 1, 2 and 3. We know that for a uniformly charged plane sheet of charge, the electric field strength E at some distance away from it is equal to sigma by 2 epsilon naught. Let this be equation 2. We use this result to calculate the net electric field strength in regions 1, 2 and 3. In region 1, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed away from the positive plate and towards the left. We also see that due to the negative plate of the capacitor, the electric field strength E is also equal to sigma by 2 epsilon naught, and directed towards the negative plate and towards the right. Hence, in region 1, the net electric field strength E naught is equal to sigma by 2 epsilon naught minus sigma by 2 epsilon naught, which is equal to 0, since the two electric fields are oppositely directed. Now let us look at the region 3. In the region 3, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed away from the positive plate and towards the right. We see that due to the negative plate of the capacitor, the electric field strength E is also equal to sigma by 2 epsilon naught, and directed towards the negative plate and towards the left. Hence, in the region 3, the net electric field strength is equal to plus sigma by 2 epsilon naught minus sigma by 2 epsilon naught, which is equal to 0. Since the two electric fields are oppositely directed in region 3 as well. Now let us look at region 2 between the plates of the capacitor. In region 2, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed away from the positive plate and towards the right. we also see that due to the negative plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught. And directed towards the negative plate and towards the right. The region 2, which is in between the plates, has two electric fields of equal magnitude, sigma by 2 epsilon naught, which are both pointing towards the right. Hence, in the region 2, the net electric field strength E naught is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. On simplification, we get E naught is equal to sigma by epsilon naught. Let this be equation 3. Let the potential difference between the positive and the negative plates be equal to V. For a uniform electric field of strength E between the plates of the capacitor, we have V is equal to E naught D. Let this be equation 4. Substituting equation 3 in 4, we get V is equal to sigma D by epsilon naught. But we know that the charge density sigma is equal to Q by A. Therefore, we have V is equal to QD by A epsilon naught. Let this be equation 5. Now, capacitance of a parallel plate capacitor C is equal to Q by V. Let this be equation 6. Substituting equation 5 in 6 and simplifying, we get capacitance C is equal to epsilon naught A by D. Let this be equation 7. This expression for the capacitance shows that the capacitance is directly proportional to the area of the plates A. And inversely proportional to the distance between the plates. We know that the capacitance of a capacitor not only depends on the geometry of the plates, the distance between the plates, but also depends on the dielectric medium between the plates. When there is no medium between the plates, let the potential difference between the plates be V naught. The electric field strength be E naught, and let its capacitance be C naught. We know that the capacitance C naught is equal to Q by V naught. Let this be equation 8. The electric field strength E naught is equal to sigma by epsilon naught. Let this be equation 9. The capacitance C naught is equal to epsilon naught A by D. Let this be equation 10. After disconnecting the charging battery, let a dielectric medium fill the intervening space between the plates of the capacitor. The dielectric medium in between the plates will be now in the presence of the electric field in between the plates. We know that when a dielectric medium is in an external electric field, it is polarized. The net effect on the dielectric is that there is an induced positive charge density plus sigma dash on the right face and minus sigma dash on the left face. Due to this, there is a weak induced electric field, say E dash, in the direction opposite to that of E naught, since the dielectric material has lesser number of free charge carriers as compared to the metal plates, which are conductors. Then, according to Gauss' law, the electric field strength E in the dielectric will be E is equal to sigma minus sigma dash by epsilon naught, which is less than the magnitude of E naught. The potential difference between the plates V is equal to ED, which now becomes V is equal to sigma minus sigma dash into D by epsilon naught, and hence V is less than V naught. In the case of linear dielectrics, sigma dash will be proportional to the external electric field strength E naught. But since E naught is equal to sigma by epsilon naught, it implies that the value of sigma minus sigma dash is proportional to the sigma value. Or we can say that sigma minus sigma dash is equal to sigma by K, where K is a constant of proportionality which is called the dielectric constant of the medium. Since the electric field strength E is less than E naught, and hence potential difference V is less than V naught, this clearly implies that the value of K must be greater than 1. For any dielectric medium other than air, K is greater than 1. Using sigma minus sigma dash equal to sigma by K in the expression for V, we get V is equal to sigma d by K epsilon naught. But since sigma is equal to Q by A, we have V is equal to Qd by AK epsilon naught. Therefore, the capacitance with a dielectric medium is C dash equal to Q by V. Here, it is of importance to note that since the charging battery is disconnected, the charge on the capacitor remains constant even after the introduction of the dielectric. Now substituting value of V in the expression for C dash and simplifying, we get C dash is equal to K epsilon naught A by D. Here, the value of K epsilon naught is called epsilon, where epsilon is called permittivity of the medium. For air, the dielectric constant K is equal to 1. Hence, we have epsilon equal to epsilon naught for air. For dielectrics other than air, we have the dielectric constant K greater than 1. The dielectric constant K of the medium is defined as the ratio of the permittivity of the medium epsilon to the permittivity of the free space epsilon naught. We know that C naught is equal to epsilon naught A by D. Hence, we can write C dash is equal to K C naught. Since K is greater than 1 for any medium other than air, we have C dash greater than C naught. We can also write K as the ratio of C dash to C naught. Thus, the dielectric constant K is a dimensionless quantity and has no unit since it is a ratio between similar quantities. Dielectric constant is also called as the relative permittivity of the medium and is also denoted by epsilon r. K is also known as the factor by which the capacitance increases when a dielectric medium fills the intervening space between the plates of the capacitor. Therefore, we see that by introducing a dielectric medium between the plates of the capacitance of the parallel plate capacitor increases. To obtain an expression for the energy stored in a capacitor, let us consider a parallel plate capacitor having metal plates X and Y, each of area A and separated by a distance D. When the plates X and Y of the capacitor are connected to a battery, one of the plates is given an excess charge plus Q and the other is given a charge minus Q. The plates X and Y are connected to the positive and the negative terminals of the battery, respectively. Let the capacitance of the capacitor be C, which is a constant. Let us now try to understand the mechanism involved in the process of charging of the capacitor plates from an energy point of view. In order to do that, we need to first imagine that the plates of the capacitor are completely uncharged. Now imagine removing infinitesimally small positive charge plus dq dash from the plate Y and transferring it to the other plate repeatedly. In this process, we see that the plate Y is getting negatively charged due to the buildup of excess negative charge on it, and hence the plate Y is at a lower potential. Simultaneously, we see that the plate X is getting positively charged due to the buildup of excess positive charge on it, and hence the plate X is at a higher potential. Therefore, the process involves transferring charge from the plate Y at the lower potential to the plate X at the higher potential. The electric field that builds up between the plates has a direction that tends to oppose further charge transfer. In other words, we can say that there exists a force that repels the transfer of charge plus dq dash repeatedly to plate X. Therefore, as charge accumulates on plate X, this repulsive force on the charges being transferred increases, and hence the amount of work done to transfer charge also increases. This work is actually done by the battery at the expense of its stored chemical energy. The work done to charge a capacitor is stored as electrostatic potential energy, U, in the capacitor. Now, let us consider a state of the capacitor where the charge on the plates of the capacitor is Q dash and the potential difference between the plates of the capacitor is V dash. Then, Q dash is equal to CV dash or V dash is equal to Q dash by C. Let this be equation 1. Now let us transfer the next additional charge plus dq dash to the plate X of the capacitor from the plate Y, and let the work done in the process be dW. From the definition of potential difference, we know that V is equal to dW by dQ. Therefore, dW equal to V dash dQ dash. Let this be equation 2. Substituting equation 1 in 2, we get dW is equal to Q dash by C into dQ dash. Let this be equation 3. Now, let us calculate the total work done W to charge the capacitor from 0 to a total charge plus Q. We know that W is equal to integral dW in the limits 0 to plus Q. Substituting the value of dW from equation 3 in the above expression and simplifying further, we get W is equal to Q square by 2C. This work done, W, is stored as electrostatic potential energy in the capacitor. Electrostatic potential energy of the capacitor is denoted by U. Hence, we get U is equal to Q square by 2C. Using Q equal to CV, we also see that energy stored U is equal to Q square by 2C is also equal to half CV square. Now, since Q is equal to CV, U is equal to half QV. A charged capacitor is analogous to a stretched spring. When the spring is stretched, it stores elastic potential energy, U, equal to half kx square, where k is the force constant of the spring and x is the elongation in the spring. When released, the spring loses the stored elastic potential energy. Similarly, the capacitor when charged stores electrostatic potential energy U equal to Q square by 2C. We see that the value of Q is analogous to the elongation x, and the value of 1 by C is analogous to the value of the force constant K. The energy supplied to the capacitor in the charging process is released when the capacitor discharges. We can also say that the energy stored in the capacitor is localized in the electric field between the plates. Now let us derive an expression to calculate the energy density of the region between the plates of the capacitor. The electric field strength E between the plates of the capacitor is equal to V by D, assuming a uniform electric field between the plates. Let this be equation 4. The electric field fills the region between the plates, and this region has a volume equal to area A into distance D. The energy density is defined as energy stored per unit volume. Therefore, energy density is equal to the energy stored by volume. This is equal to half CV square divided by AD, since the volume is equal to AD, which is equal to CV square by 2AD. Multiplying and dividing the right-hand side of this expression with D, we get energy density is equal to half CD into V square by AD square. Let this be equation 5. For a parallel plate capacitor, we know that the capacitance C is equal to epsilon naught A by D. Therefore, CD by A is equal to epsilon naught. Let this be equation 6. Substituting equations 6 and 4 in equation 5 and simplifying, we get energy density is equal to half epsilon naught into E square. This equation for energy density holds good for the electric field of any charge configuration in general. Consider an electric dipole consisting of charges plus Q and minus Q, separated by a small distance 2a, with its axis placed along the x-axis and the midpoint of the axis of the dipole at the origin. The charge plus Q lies on the positive x-axis at A, and the charge minus Q lies on the negative x-axis at B. The electric dipole moment P due to the dipole is equal to 2AQ, and the dipole moment P points from minus Q towards plus Q. Let this be equation 1. Consider a point P in the electric field of the dipole in free space, at a distance r1 from the charge plus Q, and distance r2 from the charge minus Q. The net electric potential at point P due to the electric dipole is equal to the algebraic sum of the electric potentials due to the charges plus Q and minus Q of the dipole. And is equal to 1 by 4 pi epsilon naught into Q by R1. Similarly, the electric potential at point P due to the charge minus Q is V2 and is equal to minus 1 by 4 pi epsilon naught into Q by R2, since the charge itself is negative. According to the principle of superposition, the net electric potential at point P due to the electric dipole is denoted by V, which is equal to V1 plus V2. Substituting the earlier expressions for V1 and V2 in the equation for V, and simplifying, we get the net electric potential V is equal to Q by 4 pi epsilon naught into 1 by R1 minus 1 by R2. Let this be equation 2. Theta is the angle made by line OP with the direction of the electric dipole moment. From the geometry of the figure, using the cosine rule for the triangle PAO, we have R1 square is equal to R square plus A square minus 2AR cos theta. This can be written as R1 square is equal to R square into 1 minus 2A cos theta by R plus A square by R square. Let this be equation 3. If R is much greater than A, then the ratio A to R is much less than 1, and hence the term A square by R square in equation 3 can be neglected as it becomes very negligible. Then we get R1 square is equal to R square into 1 minus 2A cos theta by R. This implies R1 is equal to R into 1 minus 2A cos theta by R power half. Therefore, 1 by R1 is equal to 1 by R into 1 minus 2A cos theta by R power minus half. Using binomial expansion of the terms in parentheses, we get 1 by R1 is equal to 1 by R into 1 plus A cos theta by R. Let this be equation 4. Similarly, using the cosine rule for triangle PBO, we have R2 square is equal to R square plus A square plus 2AR cos theta. This can be written as R2 square equal to R square into 1 plus 2A cos theta by R plus A square by R square. Let this be equation 5. If R is much greater than A, then the ratio A to R is much less than 1, and hence the term A square by R square in equation 5 can be neglected since it becomes negligible. Then we get R2 square is equal to R square into 1 plus 2A cos theta by R. This implies R2 is equal to R into 1 plus 2A cos theta by R power half. Thus, 1 by R2 will be equal to 1 by R into 1 plus 2A cos theta by R power minus half. Using binomial expansion of the terms in parentheses, we get 1 by R2 is equal to 1 by R into 1 minus A cos theta by R. Let this be equation 6. Substituting equations 4 and 6 in equation 2 and simplifying, we have V is equal to 1 by 4 pi epsilon naught into Q by R into 2A cos theta by R, which will be equal to 1 by 4 pi epsilon naught 2A Q cos theta by R square. We know that the dipole moment P is equal to 2AQ, and hence net potential V is equal to 1 by 4 pi epsilon naught P cos theta by R square. Let this be equation 7. If R cap is the unit vector along the direction of OP, and since P dot R cap is equal to P cos theta, then we have net potential V is equal to 1 by 4 pi epsilon naught into P dot r cap by r square. The potential V as obtained by equation 7 is for the distance r, which is very large compared to A. If we consider point P on the positive x-axis, then the angle between the position vector of point P and the dipole moment of the dipole is 0. Then the potential at P due to the dipole V is equal to 1 by 4 pi epsilon naught into P by r square, as cos 0 degrees is equal to 1. If point P is on the negative x-axis, then the angle between the position vector of P and the dipole moment of the dipole is 180 degrees. The potential at P due to the dipole is V is equal to minus 1 by 4 pi epsilon naught into P by r square, as the cosine of 180 degrees is minus 1. For any point on the equatorial plane of the dipole, the net potential will be 0. Since plus Q and minus Q cause equal positive and negative potential respectively on the plane, and as theta is equal to 90 degrees. Therefore, cos 90 degrees is equal to 0. When the position vector r is rotated about the dipole moment vector P, keeping the angle theta fixed, then the points corresponding to P on the cone generated will have the same electric potential. We also observe that the electric potential V due to the dipole is inversely proportional to the square of the distance of the point of observation in the electric field of the dipole. In the case of a dipole, we have calculated the net potential due to a system of two charges. Now, let us consider the electric field due to a system of charges. Say, Q1, Q2, Q3, and so on up to Qn. Let us consider a point P in the electric field of the charge configuration. Let the distances of Q1, Q2, Q3, and so on up to Qn from point P be R1, R2, R3, and so on up to Rn respectively. The potentials due to Q1, Q2, Q3, and so on up to Qn at point P in the electric field are represented by V1, V2, V3, and so on up to Vn respectively. Since electric potential is a scalar quantity, the net electric potential V at point P will be equal to the algebraic sum of the potentials due to the individual charges. Thus, it is V is equal to V1 plus V2 plus V3 and so on up to Vn. Substituting the expressions for the potential at point P due to individual charges, we get V is equal to 1 by 4 pi epsilon naught into Q1 by R1 plus Q2 by R2 plus Q3 by R3 and so on up to Qn by Rn. Let this be equation 8. to obtain the potential due to a continuous charge distribution, we first divide it into a number of small volume elements of charge density ρ, such that the small volume elements have a volume dV each and a charge ρdV each. Then we find the potential due to each such volume element, say dV'. Then the potential V due to entire charge distribution is then obtained by integral dV', since this gives the sum of potentials over all such distributions. Now let us look at an example of uniform charge distribution. Let us consider a uniformly charged spherical shell of radius r, with a charge q distributed over its surface. For any point P, which is at distance r greater than r, we have the potential due to the spherical shell at that point as V is equal to 1 by 4 pi epsilon naught q by r. This equation holds good for all points that lie on the sphere or outside the sphere. Let this be equation 9. Since the electric field strength E for all points inside the spherical shell is 0, the electric potential has to be constant for all such points. The electric potential at any such point which is inside the surface will be equal to the potential on the surface, and will be equal to 1 by 4 pi epsilon naught q by r. We know that the work done by an external force to bring a charge q0 from infinity to a point in the electric field of any charge distribution is equal to the electrostatic potential energy of the charge q0 at that point. That is, the work done to bring the charge q0 from point S at infinity to P is equal to the potential energy of q0 at point P. Since the force on charge q0 due to any static charge configuration is F equal to q0 E, the work done will be proportional to q0. We can say that W is equal to a constant K into q0, or the quantity W by q0 is equal to K. Therefore, the resultant quantity obtained is independent of q0. The work done per unit test charge is a characteristic of the electric field at that point due to the charge configuration, and is known as electric potential at that point in the electric field due to the charge configuration. The electric potential is denoted by V. Let us consider a point P between the origin and point S. Then, potential energy of the charge q0 at points S and P is US and UP respectively. We know that the work done by the external force to bring charge q0 from point S to P is expressed as WSP is equal to delta U, which is equal to UP minus US. If VP and VS denote the electric potentials at points P and S respectively, then the work done by the external force to bring the unit positive charge from S to P is equal to VP minus VS, which is in turn is equal to UP minus US by Q0. Choosing S to be at infinity and also the electric potential at infinity as 0, the work done by the external force to bring the unit positive charge from infinity to point P in the electric field is equal to the electric potential Vp at point P. The electric potential V at any point in the electric field of a charge configuration is equal to the work done to bring a unit positive charge from infinity to that point in the electric field. Let us obtain an expression for the electric potential V at a point in the electric field of a point charge Q at the origin using the definition of the electric potential V at a point in the electric field of a static charge configuration. Consider the electric field of charge Q, in which P is a point at distance r from it. Consider the point S in the electric field, which is at distance r' from the charge Q. Let a unit positive charge Q0 with a charge of +1 coulomb be placed at point S. The electrostatic force Fe between Q and a unit positive charge placed at S will be equal to 1 by 4 pi epsilon naught into Q into 1 by r' square into r' cap, where r' cap is the unit vector along the direction of OS. Therefore, Fe will be equal to 1 by 4 pi epsilon naught into Q by r' square into r' cap. Let this be equation 1. Now let us move the unit positive charge from S towards P in the electric field by a small distance dr', and let dW be the work done in the process. The external force F required to move the unit positive charge is equal and opposite to the electrostatic force Fe. dW will be equal to F dot dr', which is equal to -1 by 4 pi epsilon naught Q by r' square into dr'. Let this be equation 2. We observe from equation 2 that the value of dW is negative, since charge Q0 is moved against the direction of the electric field. Now let us assume that the unit positive charge is brought from infinity to point P in the electric field. And let work W be done for this process. Then W is equal to integral dW. Let this be equation 3. Substituting the value of dW, we get W is equal to minus integral 1 by 4 pi epsilon naught Q by r' square into dr' in the limits ranging from infinity to r. Let this be equation 4. Since 1 by 4 pi epsilon naught Q are constants, and evaluating only the integral, we have integral 1 by r' square dr' in the limits infinity to r is equal to -1 by r' in the limits infinity to r, which is equal to 1 by r minus 1 by infinity. On further simplifying, we get W is equal to 1 by 4 pi epsilon naught Q by r. Let this be equation 5. This is the expression for the work done to bring a unit positive charge from infinity to r, which is equal to the electric potential V at point P. Therefore, the electric potential V at point P is equal to 1 by 4 pi epsilon naught Q by r, which is the expression for electric potential at P in the electric field of the point charge Q. Let this be equation 6. The electric potential V is a scalar quantity, and its SI unit is joule per coulomb or volt. 1 joule per coulomb is equal to 1 volt. We know that the electric field E of a point charge Q at a distance r from it is inversely proportional to the square of the distance r from it. The graph shows the variation of electric field E with respect to r. The electric potential V at a point in the electric field of a point charge is inversely proportional to the distance r from the charge as seen earlier. The graph shows the variation of the electric potential V with respect to distance r from the charge. The electric potential V at a point in the electric field can be positive or negative. This can be understood from the following solved examples. A point charge of 1 microcoulomb exists in air. Find the electric potential due to the charge at a distance of 10 centimeters from the point charge. Given that charge Q equal to 1 microcoulomb equal to 1 into 10 raised to the power minus 6 coulomb. Distance from the charge is r equal to 10 centimeter equal to 0.1 meter. The electric potential due to the point charge at distance r from it can be calculated using the formula V is equal to 1 by 4 pi epsilon naught into Q by R. The value of 1 by 4 pi epsilon naught is equal to 9 into 10 raised to the power 9. Substituting the values and calculating for V, we get electric potential V due to the charge at distance R equal to 9 into 10 raised to the power 4 volts. Solved example 2. Two charges, 2 microcoulomb and minus 4 microcoulomb, are separated by a distance of 20 centimeter in air. Find the electric potential at the midpoint of the line joining the two charges. Solution. Given charge Q1 is equal to 2 microcoulomb equal to 2 into 10 raised to the power minus 6 coulomb. Charge Q2 is equal to minus 4 microcoulomb equal to minus 4 into 10 raised to the power minus 6 coulomb. The distance of the midpoint from Q1 as well as Q2 is equal to R is equal to 10 centimeter is equal to 0.1 meter. At the midpoint of the line joining the charges, the potential is V is equal to 1 by 4 pi epsilon naught into Q1 by R plus Q2 by R. Substituting the values of the various given quantities and simplifying, we get V is equal to minus 18 into 10 power 4 volt. Consider an equatorial plane of the electric dipole as shown. For various points like A, B and C, let the potentials be VA, VB and VC respectively. Electric potential due to a dipole is given by V is equal to 1 by 4 pi epsilon naught into P cos theta by R square. Since points A, B and C lie on equatorial plane, theta is 90 degrees for points A, B and C. Therefore, VA, VB and VC are equal to 0. Now let us consider a uniformly charged spherical shell of radius r with charge Q on it. Imagine a sphere of radius r around the shell. The electric potential V for any point on the imaginary sphere is given by V equal to 1 by 4 pi epsilon naught Q by R. In the above examples, we have seen surfaces which have the same potential at all points on them. Hence, potential difference delta V between points on an equipotential surface is 0. A surface on which the electric potential is the same for all points on it is called an equipotential surface. As potential difference delta V is equal to 0 between any two points on an equipotential surface, therefore, to move a test charge Q0 on the equipotential surface, the work done W is equal to Q0 into delta V is equal to 0. The equipotential surface at a point is always normal to the electric field at that point in the electric field for any charge distribution. Let us now look at some examples of equipotential surfaces. Assume a uniform electric field along the positive x-axis. Then, the planes parallel to the YZ plane represent equipotential surfaces. The concentric spheres around the charges in a dipole represent equipotential surfaces. The equipotential surfaces for a charge configuration consisting of two identical charges, minus Q each, is shown. Consider two equipotential surfaces represented as A and B in a uniform electric field of strength E, separated by a small distance delta R. Let the potentials at A and B be VA and VB respectively. Let us consider a unit positive charge Q0 on the surface A. Suppose the unit positive charge is displaced from surface A to surface B in the direction of the electric field. The work done by the electric field W is equal to F delta R, where F is the force due to the electric field on the unit positive charge. As F is equal to Q0 E, and in this case, test charge Q0 is equal to plus 1 coulomb, we can say F is equal to E. Therefore, the work done W is equal to E delta R. Let this be equation 1. According to the definition of potential difference, the potential difference delta V is equal to VB minus VA, which is equal to the change in potential energy delta U of the unit positive charge while moving from A to B. Let this be equation 2. Now, delta U will be equal to minus W since there is a decrease in the electrostatic potential energy of the unit positive charge while moving from A to B. Substituting the value of W in the above equation, we get delta U equal to minus E delta R. Let this be equation 3. Equation 2 becomes delta V is equal to minus E delta R. Therefore, E is equal to minus delta V by delta R. Let this be equation 4. Equation 4 implies that in the direction of the electric field, the potential always decreases. Thus, VA is greater than VB. It also means that in a uniform electric field, the electric field strength is equal to the potential change per unit displacement, normal to the equipotential surface at that point. Now let us learn about the electrostatic potential energy of a system of charges. Consider a charge Q1 and let P be a point in the electric field of Q1 at a distance of r from the charge. The electric potential at P due to the charge Q1 is equal to V1, equal to 1 by 4 pi epsilon naught into Q1 by R. Let this be equation 5. Now, to bring a charge plus Q2 from infinity to point P in the electric field against the electrostatic force, the work done W is equal to Q2 V1. Let this be equation 6. Substituting equation 5 in equation 6, we have W equal to 1 by 4 pi epsilon naught into Q1 Q2 by R. This work done against the electrostatic force is stored as electrostatic potential energy U in the system of charges. Electrostatic potential energy U stored in the system of charges is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R. Let this be equation 7. From equation 7, we see that the electrostatic potential energy is independent of the spatial location of the charges in a given medium, and is mainly dependent on the separation R between the charges. The electrostatic potential energy is a scalar quantity and can be positive or negative depending on whether the product Q1, Q2 is positive or negative respectively in the equation 7. When both the charges are either positive or negative, the electrostatic potential energy is positive. That is, the work done to bring a charge Q2 from infinity to point P is positive. Also, when the charges Q1 and Q2 are unlike, then the work done to bring Q2 from infinity to point P is negative. Equation 7 gives the electrostatic potential energy for a pair of charges Q1 and Q2. Proceeding similar to the above procedure, for a system of 3 charges Q1, Q2 and Q3, there would be 3 pairs in the expression for the electrostatic potential energy U, given as U is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q3 Q1 by R13, where R12 is the separation between Q1 and Q2. R23 is the separation between Q2 and Q3. And R13 is the separation between Q3 and Q1 respectively. Let this be equation 8. Equation 8 can be expressed as U equals to 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus 1 by 4 pi epsilon naught into Q2 Q3 by R23 plus 1 by 4 pi epsilon naught into Q1 Q3 by R13. This equation can again be written as U is equal to U12 plus U23 plus U13. Let this be equation 9, where U12, U23 and U13 are the electrostatic potential energies for the pairs of charges Q1, Q2, Q2, Q3 and Q1, Q3 respectively. The above procedure can be adopted for calculating the electrostatic potential energy of a system of n charges as well. From the above discussion, we see that the potential energy of a system of charges is a characteristic of its present state only. We know that electrostatic potential energy U for a system of 3 charges Q1, Q2 and Q3 can be calculated using the formula U is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q3 Q1 by R13, where R12 is the separation between Q1 and Q2. R23 is the separation between Q2 and Q3, and R13 is the separation between Q1 and Q3 respectively. Let this be equation 1. Equation 1 can also be written as U is equal to U12 plus U23 plus U13. Let this be equation 2. In equation 2, U12, U23 and U13 are the electrostatic potential energies for the pairs of charges Q1, Q2, Q2, Q3 and Q1, Q3 respectively. Let us now derive an expression for the electrostatic potential energy of the system of charges in terms of the potentials. Let V be the potential at a point P1 in the electric field E produced by a source charge. Here, R1 is the position vector of the point with respect to the origin. Let us consider a charge Q1 at infinity from point P1. If W1 is the work done to bring the charge Q1 from infinity to the point P1 in the external field, then the external electric potential at the point P1 is V of R1 equal to W1 by Q1. This implies that W1 equal to Q1 into V of R1. Here, we assume that the potential due to the source charge at infinity is 0. This implies that V of R1 is also the potential difference between the point and infinity, which is delta V. Now, if Q1 is released at point P1, it moves away in the direction of the electric field to infinity and gains kinetic energy equal to W1 when it reaches infinity. If V of R1 is plus 1 volt, then the potential difference between the point P1 and infinity is delta V equal to V of R1 minus V infinity, which is equal to plus 1 volt. Now, if Q0 is an electron which is at rest at infinity, is released under a potential difference, then it moves towards the point P1. Since P1 is at higher potential compared to the point at infinity, the electron gains kinetic energy, which is equal to Q0 into V of R1. The magnitude of the charge on the electron is 1.6 into 10 power minus 19 coulomb, and V of R1 is equal to 1 volt. Therefore, the kinetic energy gained will be equal to 1.6 into 10 power minus 19 joule. This kinetic energy gained by the electron is called 1 electron volt. Electron volt is defined as the kinetic energy gained by an electron when accelerated under a potential difference of 1 volt. We have seen that the work done to bring a charge Q1 from infinity to point P1 is given by W1 is equal to Q1 into V of R1. Now let us consider another point P2 in the electric field, whose position vector with respect to the origin is R2, and the external potential at the point is V of R2. Let the distance between points P1 and P2 be R12. Let us bring another charge, Q2, from infinity to the point P2 in the electric field, and let the work done in this process be W2. Hence, work done to move the charge Q2 from infinity to the point P2 is Q2 into V of R2. If Q2 is now released, it moves due to electric field E and also due to the electric field of Q1. Work has to be done to hold the charge Q2 against the force due to the electric field E and also due to that of Q1. Work done to hold Q2 against the electric field due to Q1 is expressed as W12, which is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12. The total work done to hold Q2 at rest at P2 is Q2 into V of R2 plus W12. Substituting the relation for W12, we have total work done is equal to Q2 into V of R2 plus 1 by 4 pi epsilon naught Q1 Q2 by R12. The total work done to assemble the system of charges in the external electric field is equal to Q1 into V of R1 plus Q2 into V of R2 plus 1 by 4 pi epsilon naught into Q1 Q2 by R12. This is stored as electrostatic potential energy in the system of charges. Let this be equation 3. Now, let us derive an expression for the electrostatic potential energy of an electric dipole in a uniform external electric field of strength E. Consider an electric dipole placed in a uniform electric field of strength E directed along the positive x-axis. The axis of the dipole makes an angle theta with the direction of the electric field. The dipole has charges plus q and minus q separated by distance 2a. Hence, its electric dipole moment P is equal to 2aq. The dipole, when placed in a uniform electric field, experiences a torque tau, which is equal to P cross E equal to P sine theta. Let this be equation 4. This torque rotates the dipole until it is aligned in the direction of the external electric field. Let us apply an external torque tau external equal and opposite to the torque tau, which rotates the dipole from the angle θ1 to the angle θ2, with the field direction without giving the dipole any angular acceleration. That is, at an infinitesimally low angular speed. Let the work done by the external torque in this process be W. Then, W is equal to integral tau external dot d theta in the limits θ1 to θ2, as tau external is equal to tau. We can write W is equal to tau into d theta in the limits θ1 to θ2, substituting tau equal to P into E sine theta. We get W is equal to integral P E sine theta d theta in the limits θ1 to θ2. Since P and E are constant, we keep them out of the integration, and thereby, carrying out the integration, we get W is equal to minus PE into cos θ2 minus cos θ1. This work done by the external torque gets stored as potential energy U in the system in the external electric field. If θ1 is equal to 90 degrees and if θ2 equal to θ, then the potential energy in terms of the angle the dipole makes with the external field is U is equal to minus P into E cos θ. We can express PE cos θ as P dot E. Then, potential energy U of the dipole is expressed as U equal to minus P dot E. If V of R1 and V of R2 denote the potentials at the positions of the charges plus Q and minus Q of the electric dipole respectively, the axis of the dipole makes an angle θ with the direction of the electric field, and the distance between the charges R12 equal to 2a. Then, substituting Q1 equal to plus Q and Q2 equals to minus Q in equation 3. And simplifying, we get potential energy U of the system as U is equal to plus Q into V of R1 plus minus Q into V of R2 plus 1 by 4 pi epsilon naught into minus Q square by 2a. This equation can be further simplified as U is equal to Q into V of R1 minus V of R2 minus 1 by 4 pi epsilon naught into Q square by 2a. We can further simplify VR1 minus VR2 as follows. V of R1 will be less than V of R2, since potential decreases in the direction of the field. We can say dV is equal to V of R1 minus V of R2, which is equal to minus EdR. Since dV is equal to minus EdR, from the figure, dr is equal to 2a cos θ. Therefore, V of R1 minus V of R2 will be equal to minus 2a cos θ into E. Multiplying both sides with Q, we get Q into V of R1 minus V of R2 equal to minus Q into 2a cos θ into E. Hence, Q into V of R1 minus V of R2 can be written as minus 2aq cos θ into E. And since dipole moment P equal to 2aq, this can be written as minus Pe cos θ. Now the electrostatic potential energy of the system can be written as minus Pe cos θ minus 1 by 4 pi epsilon naught q square by 2a. If the electric dipole were perpendicular to the field direction, then the potential V of R1 will be equal to V of R2, and hence Pe cos θ will be equal to 0. And hence, the electrostatic potential energy of the system will be equal to minus 1 by 4 pi epsilon naught q square by 2a.